This conference will now be recorded.
A very good morning.
Good morning.
Good morning, Dr. Ben Blauable. Yeah, the Miriam Takoli Kagri on Yadasman.
For my presentation, you have to give me the right to share my screen.
Doctor, can you hear me?
Yes, I can,
Yeah, please go ahead with your presentation.
but I see my screen, but I cannot completely open it.
Yeah, I can see your
Oh,
PowerPoint presentation.
I'd like to make it as full screen, but I cannot see how to do this.
Yeah, below there will be an option. Just please click on that for full screen.
Where's this option? I cannot see it.
Okay, just give me a 2 minutes time. Let me introduce the.
Yeah, because I can also not, it's just I see the screen, but I'm not in the PowerPoint.
Yeah, but I can see your PowerPoint presentation.
Can you see it still? The first
Yes, yeah,
slide?
now it is full slide. Yeah.
Okay. Now I left the go to screen and turned to PowerPoint.
Yes, and please go ahead with the presentation.
Should I start?
Yes, please.
Okay, thank you so much. I'd like to thank the organizers and hello, everybody, to invite me to give a keynote presentation to this event on principles and standards to design and manage integration and interoperability for intelligent and ethical transformed health and social care ecosystems. First, I'd like to introduce what is meant with transformed ecosystems. Everyone might remember the empiric or phenomenological medicine, where domain-specific general services have been provided by the family doctor and others based on observations and justified through pattern recognitions. And everything has been stored as data on paper-based repositories or computer-based repositories. And for that reason, we introduced data standards. This was then advanced to evidence-based medicine. Again, domain-specific, group-specific services have been provided, but now the justification used information from central data repositories where other experts, domain experts, stored the outcome. And for sharing information between different institutions, we introduced information standards. Then we introduced person-centered medicine in the managed care process to provide multiple domain services. And for doing this, we had to manage processes following best medical practice guidelines. And for doing this, we introduced agreed terminologies and best practice guidelines for cross-organizational business processes. And for doing this, we advanced from information standards to terminology standards and process standards. Then we introduced personalized medicine, providing multiple domain services, thereby interrelating the different domains and disciplines, considering the pathology of diseases and justifying everything through clinically justified individual status and context. For doing this, we had to represent disciplinary concepts in situational contexts, and for doing this, we advanced to knowledge management based on domain ontology standards. And now we arrived at 5P medicine, providing cross-domain services, including consumerism and telemedicine, thereby interrelating all disciplines and enabling comprehensive communication and cooperation. That means mutual understanding, and thereby also understanding the health process, understanding the biophysics, the biochemistry, the pathology, physiology, and all the other issues. And for doing this, we considered the scientifically justified individual status based on multidisciplinary concepts in comprehensive context. And for doing this, we had to manage many different knowledge spaces from each of the domains involved based on multiple ontologies and guided by top-level ontology standards. The healthcare transformation towards personalized, preventive, predictive, participative precision medicine considers the individual health status, conditions, genetic and genomic dispositions in comprehensive, that means personal, social, occupational, environmental, and behavioral context. This requires the advancement for communication and cooperation among all the different business actors coming from different domains and therefore using different methodologies, terminologies, and ontologies, and individually showing different education skills and experiences. And as different domains are using the same data to represent different concepts, we had to advance from data level to concept or knowledge level. The challenge there is the understanding and formal and consistent representation of our 5P medicine ecosystem. That means a multidisciplinary dynamic system in variable context. So we can then map between the different disciplines and methodologies, perspectives, and intentions, and really understand the situation and the processes. If you don't understand the components, functions, and relations of that 5P medicine ecosystem in the real world business viewpoint, we cannot properly model and formalize the integrated and interoperable ecosystem, and we can also not formulate the requirements and the design for correct solutions, that means the related e-health solutions. Furthermore, we cannot decide on correct integration and interoperability at data level. We have to do it on a real-world business system level. The objective of 5P medicine is providing health services everywhere and anytime. Thereby, we have to individualize the system according to the status, context, needs, expectations, wishes, and environments of the subject of care. Thereby, we have to integrate the different actors from different disciplines, including the participation and especially the empowerment of the subject of care, thereby allowing all of them to use their own language, methodologies, terminologies, and ontologies, and nevertheless comprehensively understanding each other. That means the physicist understands the chemist, the lawyer, the nurses, and also the patient understands the doctor when speaking Latin without any requirements. And this allows the usability and acceptability of 5P medicine solutions. As mentioned, we cannot stay at the data level. That means interpreting symbols and the syntax as data, the semantics as information, and the pragmatics as knowledge. We have also to take the right decision for the right actions. And therefore, we have to advance from data space and information space to knowledge spaces. And this requires also another approach regarding interoperability. Everyone might remember the technical interoperability level, enabling lightweight interactions between two devices or two applications based on technical plug and play and signal and protocol exchange. Then we advanced to structural interoperability for data sharing based on simple electronic data interfaces and envelopes. Then we advanced to syntactic interoperability for information sharing based on messages and clinical documents with agreed vocabularies. And then we advanced to semantic interoperability for knowledge sharing at IT concept level based on advanced messaging with common information models and agreed terminologies. But for 5P medicine, this is not enough. Here we have to enable organization and service level interoperability to enable knowledge sharing at business concept level for agreed corporations in a common business process. Furthermore, we have to realize knowledge-based interoperability for knowledge sharing at domain level for cross-domain cooperation, that every domain expert understands the other side without first studying that domain to enable multi-domain processes. And individually, we have to enable skills-based interoperability for knowledge sharing in individual context for individual engagement in multiple domains, guaranteeing that everyone can communicate and cooperate with the other side. Currently, we focus on data level interoperability, but this is not enough. We have to provide knowledge level interoperability to share between different knowledge between different domains and disciplines, and also integrating different products, artifacts, standards, etc., for comprehensive solutions. Thereby, it is impossible to represent such highly complex, highly dynamic, multidisciplinary, multi-domain 5P medicine system just by one domain's terminology. We have to represent all the different domain concepts based on a hierarchical set of ontologies. For representing the advanced interoperability setting, we have to guarantee that all the different representations are linked to the same real-world component, that everyone is talking about the same issue. For that reason, I have developed an abstract and generic reference architecture to represent any viewpoint or domain of interest. For representation, we could use universal type theory, but I introduced a systems-oriented ontology-based representation to represent any language, any context, etc. Currently, this is done based on implicit knowledge represented by ICT representation tools. That means believing that this data representation meets all the requirements and also meets the expectations of the actors involved. But this is not enough, and therefore I like to introduce the systems-oriented approach we are using. If we have to characterize a system, we could use the black box approach, characterizing a system through the input-output relations. But for our 5P medicine, we have to understand the system in any context at any granularity level. That means we have to deploy a white box approach, representing the healthcare ecosystem with all the departments of all the workstations, all the technical devices, all the actors involved, etc., but also the patient as a body inside the society with the organs, with the tissues, with the cells, with the molecules, with the atoms up to the level of elementary particles. And this must be done from all the different domains involved, as they have another representation and understanding of those issues. For doing this, I developed in the 90s, last century, the generic reference architecture representing any system from the perspective of all the involved domains at different granularity levels, starting with basic concepts such as the cells, the basic services and functions such as the tissues, the operations in the cell, and then the relation networks in the organ and the system concepts in the body, from the perspective of biophysics, biochemistry, social sciences, different medical specialties, legal affairs, etc. The challenge thereby is the formalization of knowledge, the development of formalized and accepted ontologies, as well as the decentralization of knowledge and decision support supported by tooling and mapping mechanisms. For doing this, we have to distinguish three different levels of knowledge representation. One is the domain-specific model for each domain, also called the epistemological level, as we know from the handbooks of the different specialties, the handbook of physics, the handbook of mathematics, etc., representing that domain. Then we have to manage the notation level. That means the proper concept representation and formalization to map them. And of course, we have to manage the processing level for implementation. And if I'm talking about the model, I'm always talking about the representation of objects, their properties, relations, and interactions within one domain to enable a related business process. And in 5P medicine, we have to do it for many domains for interrelated business processes. The generalization of domain-specific epistemological models using the different domain ontologies requires the transformation of that representation into universal knowledge representation notation, so we can map the chemical aspects, the biophysical aspects, the social issues, the different clinical specialties, etc. And of course, we have to validate this specification on the real world system. If we are talking about a model, we have to provide an ambiguous, abstract conception of parts of the reality. And this must be defined by the relevant stakeholders for each of the domains, providing the view of the model and the way of structuring and naming the concepts. That means we cannot stay at the data level. We have to start with the real world domain knowledge level, and then we can transform it into IT-related specifications. That means we have to start with the very high level of the real-world business system represented through the different domain ontologies. Then we have to transform it into the IT 5P medicine ecosystems representation using BPML. Then the logical representation of all the different elements using information representation, and finally the physical representation based on data standards. One aspect of knowledge representation is the expressivity of that tool. Of course, we have finally for implementing to look for highly expressive knowledge representation to express facts or issues based on simple semantics and grammar of that knowledge representation resulting in yes or no bits and bytes. However, such highly expressive language requires complex logic and algorithms to construct equivalent interferences for representing the real-world scenario. Only the real-world scenario, that means the highly expressive knowledge representation, the less expressive knowledge representation is complete and decidable. That means we have to start with the business systems experts, the actors, and then we can transform it into the IT systems representation, the informational representation, and finally the implementable data representation. Of course, any system can be represented using ICT ontologies, but for justifying correctness and completeness of our components in our system regarding structure and behavior, then we have to start with the business viewpoint based on domain ontologies, justifying structure and behavior, etc. And then we can refine it and develop our system. And from that perspective of an overarching consideration, natural language is not just sufficient to represent meaning, shared knowledge, and skills. It provides also an optimum between the restrictions to special structure and generative power, data representation or information representation, and the decidable representation of real-world concepts. And here you can see the existing ontologies. There we have formal ontologies to represent the reality based on general logic, model logic, description logic, first-order logic, etc. Then we have to transform it into informational representation based on glossaries and thesauries, terms representation, and finally we have to implement it based on metadata and data models, database schemas, etc. An ontology describes the single concepts or the entities of the knowledge space. That means the different elements and what the underlying knowledge is. The entity could be contingent, that means static or occurrent, dynamic. The contingents could be independent contingent, generically dependent contingent, specifically dependent contingent, while the occurrence could be process depending, process boundary depending, temporal region depending, and special temporal region depending. And then it can be refined up to the level of elementary particles, so we can represent the specific domain. And if you have a domain where no ontology so far exists, you can use this basic formal ontology standardized in ISO 21838 as intermediate solution. And then it is also transferred into the real world scenario. As you can see, that means the independent, the granularity level are organs, organisms, cells, molecules. The independent are organisms, cells, and molecules. The dependent are organ functions, cellular functions, and molecular functions. And the occurrents are processes. For realizing this approach and managing the definition and the implementation of appropriate solution, I developed the interoperability and integration reference architecture model and framework, which provides a generic specification to manage interoperability and integration in any system, dynamic, complex, context-aware, multidisciplinary systems of systems. And this is applicable to healthcare, where it is presented now, but you can also use it for nanotechnology, space physics, environmental science, whatever. And this is also the reason that I receive daily more than 150 invitations for keynotes from around the world. In that context, we are defining in this standard basic principles and paradigms to represent and manage any system in the sense of a meta-architecture, thereby using type theory instead of set theory, universal logics, and the representation has to start with the real world knowledge space level and then is transformed into the implementable solution. And for defining the correct model, we have to deploy the business domain experts. They define the real world scenario, not the data experts. And therefore, if we still stay at the level of data focused interoperability, we cannot manage this challenge. The objectives are to enable communication and cooperation between different domains and also allowing to include and reuse existing standards, even old and error-prone standards, existing information components, information data elements, etc., by correctly adapting them, modifying them, and integrating them for each use case we are looking for. And thereby, we enable cross-domain concept sharing, knowledge sharing, the mapping between the different perspectives, finding the correct solution from all the different aspects and domains for this use case in this point in time, transforming into ICT relations, and then guaranteeing the correct solution. And as I said, always considering all aspects. ISO 23903 is a system-oriented, architecture-centric, ontology-based, and policy-driven approach, including the development process according to ISO 42010 and ISO 10746 of software development paradigms. And thereby, we have to extend the focus on the IT environment to start with the real-world scenario, the real-world architecture. And here you can see the ISO 10746 standard representing the enterprise viewpoint of an ICT system, the information viewpoint, the computational viewpoint, the engineering and technology viewpoint for running the solution. But we have to start representing the real world business view represented by the domain ontologies and then transforming it into ICT solutions for correct deployment. Thereby, we have to accept that we cannot interrelate between different domains just using in data interchange format, an API, application program interface, to transform the data into a standardized format as we do with HS7. No, we have to transform each of the concepts representing this based on the reference architecture model and framework of ISO 23903. And then we are able to map the biophysical, the biochemical, the clinical, the social, the legal, and other issues for each use case, in each point in time, and can map this correctly, element by element, and then transform it into correct solutions. And therefore, we extended the generic component model by the business viewpoint and represented the different knowledge, that means the business domain knowledge through the domain ontologies, the enterprise knowledge through the enterprise representation style based on BPML, the informational representation based on information standards, and the data representation based on data standards. And then we can, of course, map the different aspects, mapping the biophysics with the biochemistry, the legal affairs constraining the processes, etc., using the top-level ontology introduced before. And we can use the same for mapping the different ICT components represented by BPML, the existing informational models, the existing standards, and then we will see, oh, for this use case, this attribute is not correct, and we have to remove it, and we have to add another one, and adding new relations, etc. So we can always guarantee the correctness of our solution. And so we can solve any problem of multidisciplinary integration and interoperability, starting with the real-world scenarios, understanding each other based on ontology-based representations, then transforming it, and then looking for existing components and adapting them according to the real-world component representation and adapting them. And so, as I said, we can combine old standards and new standards, HSF version 2 and 3, and all other issues without any limitations. And here you can see we are also deploying existing standards, the reference information model, the domain message information models, and other without any relations, any constraints. And we can also adapt existing electronic health record standards, archetypes, and other components, and also other specifications for ICT solutions, such as the object management group's core architecture, the model-driven architecture, or other approaches. In summary, we started with a physical data model developed by data modelers and developers, defining implementation-related platform-specific aspects as done in ICT standards such as HS7 version 2. Then we advanced to logical data models developed by data modelers and analysts, defining layout and types of data and relations. That means representing the information viewpoint, advancing from data focus to information focus, as done in HS7 version 3, HS7 clinical information model initiatives, OpenEHR archetypes, that means components for electronic health records, etc. Next level, we introduced high-level data models, representation the related concepts and knowledge to enable relevant defined by business domain stakeholders, and they define relevant information and representation, including relationships and basic concepts, as done for example, in detailed clinical models, etc. But for 5P medicine, this is not enough. We have to map different knowledge spaces of all domains involved, including also system behavior aspects such as policy issues, ethical, security, privacy, trustworthiness, and other challenges, legal affairs. And this must be done by business domain stakeholders, defining scope requirements and related basic concepts of business cases. And only ISO 23903 defines this process. I hope it became clear interoperability is not first a matter of ICT domains. We have to focus on users and the user domains. Thereby, interoperability is the challenge to meet business objective by sharing knowledge and skills based on an hierarchical system of ontologies. Thereby, we have to go beyond simplification and abstraction for data integration towards concept and rule harmonization and integration at business domain ontology level. Multidisciplinary interoperability and integration requires an architecture-centric systems approach to the domains of discourse represented through their ontologies, thereby enabling the formalization of systems representation and the integration through ontology mapping supported by appropriate tools. Such flexible, scalable, business-controlled, adaptive, knowledge-based intelligent systems have to follow such systems-oriented, architecture-centric, ontology-based, and policy-driven approach as standardized in ISO 23903. And this is meanwhile deployed in many standards at ISO, IEC, CEN, OMG, IEEE, HS7, and is always mandatory for all projects covering more than just one domain, because in one domain, you can also agree on data representations and integrate all those things in your standard. But for multidisciplinary systems covering more than just one domain, you have to start with the concept and knowledge spaces from all the different perspectives and then transform it properly. And with this approach, we can also provide advanced security and privacy following the Data Protection Directive to the General Data Protection Regulation, requiring that we have to consider always the context of all the business processes, the intentions, objectives of the actors involved, etc. And therefore, we have to understand the system in all the details from all the perspectives in any context. Transforming healthcare towards personalized, preventive, predictive, participative precision medicine addresses health and social care supported by technologies. And I said this is applicable for any domain and any system. In this context, the deployment of edge computing, cognitive computing, artificial intelligence, and autonomous computing is crucial beside miniaturization and mobility for enabling P-health, D-health. Beside opportunities, such technologies also be risks which must be managed. Beside relations between technology and human actors considered in the past, that means the relation between the technical solution and the actor regarding security and privacy, we have also to watch the behavior of our intelligent and autonomous systems from a humanistic, moral, and ethical perspective. If we don't understand the 5P medicine ecosystem in all its components, functions, relations, we cannot properly model and formalize it, and we cannot formulate the requirements for correct solutions. And we can also not decide on correct integration and interoperability at data level. We have to do it at the real world business system level and then transforming it. And this is, of course, an educational challenge, but we do not start from scratch. Let's globally engage on 5P medicine opportunities and challenges. Thereby, we can reactivate the Enlightenment period paradigms developed some 100 years ago. For doing this, we have to understand the universe. We have to protect the earth. We have to serve the society, and we are obliged to good actions. And so I can just wish us the greatest success in this endeavor. Here are some freely available papers describing all those things in detail, but I'm always also ready for bilateral discussions. Feel free approaching me using my email address, and then we can go in all the details needed. Thank you very much for your attention. Hello? Hello?
Hello, can you hear me?
Yeah?
Yeah, there is a question from Henny Prathvi. How can healthcare organizations balance interoperability and seamless data sharing with patient privacy and ethical AI governance, especially when multiple stakeholders use different health information systems? That's her question.
Yes. First, I have to understand the real world business system. That means the care process we are looking for. Then I'm transforming it into the representation according to ISO 23903, with all the different components from the perspectives of all the involved domains. And then I'm mapping them to find a solution for each use case. Then I transform the outcome, that means the solution from all the perspectives, biophysics, biochemistry, legal constraints, whatever, into ICT representation. And then I'm reusing existing specifications and adapt them to this requirement. That means if there is, for instance, a restriction regarding the procedural policy or the legal policy, this is not allowed and this cannot be used in that context, etc., then I can always adapt this, because one of the domains I have to consider is the policy domain. I have developed the policy ontology with the different aspects, authorization, limitations, delegations, etc. And then you are transforming it into all the different viewpoints presented, reusing and adapting the existing specifications. That means if you have already a record, then you have to correct the record, adding issues, correcting other issues, removing attributes, etc. And then you can find the correct solution. And so you can integrate any existing and even error-prone solutions because they are automatically corrected in this process. Other questions?
Yes, our question, she got the answer. And yeah, any more questions? Yeah, thank you, Dr. Blobel. Thank you for the excellent presentation, and thank you.
Welcome.
Yeah, thank you for joining us today. Thank you very much. And if anyone has any questions, you can contact Dr. Blobel to his email ID, and he already showed that in the slide. Doctor, I request you to text your email ID here in the chat box, and if anyone wants to contact, they will contact you by email.
Okay.
Yeah, thank you very much, and thank you for joining us today.
Welcome.
Yeah, and we'll move on to our next presentation. I would like to call upon Dr. Kagri Un. He's from Kukurova University, Turkey, and his presentation is on low-cost polymer ceramic hybrid materials for enhancing thermal safety in electric vehicle batteries, a conceptual and modeling-based study.
Well, welcome everyone. First, I need to share my screen. Thank
Yes,
you very
please.
much. Yeah, thank you. Little bit time, sorry. Okay. I think I need to open my Chrome. Wait. Okay. I think now you're able to see my screen. Yes. Well,
Yep.
first of all, thank you very much again for the conference presenters and organizers for this very valuable conference. First of all, my name is Dr. Kagrian from Turkey. I am very happy to present you the low-cost polymer ceramic hybrid materials for enhancing thermal safety in the electrical vehicle batteries. Well, first of all, you know that electrical vehicle is a very important transportation item for nowadays. So my research focus is developing low-cost thermal barrier materials to improve the safety and reliability of lithium-ion battery systems for future electrical vehicles. So why battery safety is important? So it consists the thermal runaway risk, cell-to-cell heat propagation, fire and explosion hazards. high replacement cost, passenger and public safety impact on market acceptance. So, and also, if you take a look for the graphic, which consists the rapid growth of electrical vehicles, it is roughly the 25 million global electrical vehicle sales per year. So our key question is how can we improve the thermal safety without increasing cost, weight, and complexity? So the current engineering challenge is the modern battery packs may contain hundreds of or even thousands of individual lithium ion cells. If a single cell experiences thermal runaway, the generated heat can rapidly propagate to neighboring cells. This is a very dangerous situation, resulting in a chain reaction that may ultimately involve the entire battery module. Therefore, preventing or delaying heat propagation between adjacent cells has become one of the most important research topics in battery safety engineering. So, this is the mechanism for thermal runaway sequence. Thermal runaway, as you know, that is a self-accelerating process in which the heat generated inside a lithium-ion battery exceeds the amounts of heat dissipated to the surrounding environment. As you can see, the cell to cell heat propagation, the first thing is heat conduction, and it transfers to the neighboring cells. And the common triggers of thermal runaway, we can say electrical abuse, mechanical abuse, and thermal abuse. Unfortunately, this type of abuses may affect the starting of thermal runaway. So, what we did was this study employed a conceptual and modeling based approach to evaluate the thermal insulation performance of low cost polymer ceramic hybrid materials for lithium ion battery systems. Materials considered polymer matrix, epoxy resin, ceramic fillers, aluminum oxide, silicon dioxide. These materials were selected due to their low cost, commercial availability, high thermal stability, good electrical insulation, ease of processing. So you can see some ceramic fillers and polymer matrix. And what we did as a conceptual model, the cell is the hot situation. We covered the hybrid barrier layer. It consists epoxy, aluminum oxide, and silicium dioxide. And it turns from hot to cold. And we did the heat transfer model with using the Fourier's law equation. And our key parameters are thermal conductivity, layer thickness, contact area, and temperature differences. And what we observed was the ceramic fillers reduce the effective thermal conductivity. Thermal resistance increases with thicknesses, and heat transfer between adjacent cells decreases significantly. Higher thickness delays thermal propagation, and hybrid layer provides valuable time for safety systems. So, this conceptual and modeling-based study demonstrates that low-cost polymer ceramic hybrid materials have significant potential for improving the thermal safety of lithium-ion battery. The next phase of this research has to be include experimental fabrication of hybrid materials, thermal conductivity measurements, battery thermal runaway experiment, mechanical characterization, finite element analysis, optimization of ceramic filler concentration. So, I hope that this study will be very helpful for to establish the new methods of thermal safety management and engineering issue. Thank you very much again for to listening to me. Thank you. Yes, Sam. Thank you very much again for your attention. Thank you.
Yeah, have any questions? Yeah, there is a question from Henny Pravithvi. Since this study is currently based on conceptual modeling, what do you anticipate will be the biggest challenge when translating these results into experimental validation with real battery modules?
And exactly, I understand this question. Yes, in the experiment section, you have to do a lot of experiment. First, you need to create some procedural methods. For example, you can start with different type of abusing conditions. For example, first of all, the mechanical one. The second one is the chemical abuse types. So it, it's a kind of experimental issue, like Edison did. He did 1,000 experiments, maybe 999% was not so successful, but the remaining part is good. So yes, the next stage for me, I am working at the Adana Metropolitan Municipality and also collaborate with the fire department. Now I will start my experiments with different conditions. Thank you.
Yeah, any more questions? Yeah, thank you, Kagreun. Thank you for the wonderful
Thank you very much.
presentation,
Thank you.
and thank you very much for joining us today. Thank you very much. Yes, we'll move on to our next presentation. I would like to call upon Henny Prathivi, and she is from Universitas Negeri Yogyakarta, Indonesia. Her presentation is on the title Physical Characterization of Rhymi Fibers Modified with Maleic Acid. Henny Prathivi,
Yeah.
yeah, I permitted you to share your screen, so please share your PowerPoint presentation, please.
Sorry, could you please repeat the presentation sharing?
Yeah, it is physical characterization of Rhymi fibers modified with maleic acid.
Wait for a minute. I will share screen my file. Sorry, organizer, could you please let me to share my file?
Yes, I permitted you to share. Oh, yes, I can see it.
Have my screens full screen?
Yes, yeah, please go ahead.
Okay. Okay. Sorry for the interruption. Good afternoon from Indonesia. My name is. I will share to you my nucleic acid treatment on the physical, mechanical, and fibers. My research background is natural fiber, was researched by researcher recently, and it is, of course, environmentally friendly and needs surface treatment for better compatibility with polymers. In this research, because it has high young modulus, high tensile strength and stiffness, and then it improves the tensile and thermal properties of polymer composites. And then I use chemical treatments in order to remove impurities and non-cellulosic components and increase surface roughness for better matrix adhesion. There are some research objectives, such as the effect of malic acid treatment on the physical properties, and then the effect of malic acid treatment on the chemical properties, mechanical properties, and thermal properties, and then morphology. This is the roadmap of my research. I in 2025 I do like fumaric acid treatment on rami fibers and malic acid treatment on rami fibers. So from the base of the rami plant, uh, we degamming the brass and then make it into fiber, and then we immerse with chemical treatment. In this This is the code of my sample. UT is ceramic fiber without chemical treatment, and then the MA2, 4, 6, 8, and 10, which is different concentration of malic acid from 2 weight% until 10 weight%. I do some characterization such as diameter, weight loss, density, moisture content, FTAR, XRD, tensile, TGA, and SEM. This is and then some balance for weight loss measurement, density measurement, moisture content, FTIR, XRD, and then tensile, and TGS, SM. This is research about the chemical treatment. This is the diameter of the fiber. We can see that after the chemical treatment, the diameter is decreasing due to the chemical treatment, where the MA6 sample appears to have the 0.0548 millimeters. The reduction in diameter due to the chemical immersion process reached 23% compared to the fiber diameter without chemical treatment. At higher concentrations, 8 and sample MA10, the fiber diameter increased slightly to 0.0847 millimeter and 0.0744, which were still lower when compared to sample MA0 or without treatment. The density results show that chemical treatment causes an increase in fiber density along with an increased malic acid concentration. The highest density was achieved by sample MA6, which was 1.4267 gram per centimeter cubic, which indicates the optimal malic acid concentration in improving fiber structure. The cell structure element of natural fibers is damaged by malic acid treatment, thus increasing its density when compared to untreated fibers. However, when the malic acid concentration is further increased, 10% weight%, a decrease in density occurs. We can see from this picture, the highest density is achieved by MA6 sample. The diameter and density results is in line with the moisture content results, whereas LMA6 showed the lowest fiber resistance, which moisture content reached 68% compared to untreated fiber. However, the increase in moisture content increased when the rami fiber was soaked with such as 8 and 10 weight percent. This due to fiber swelling and the absorption phenomena. This is the XRD results where our samples demonstrated similar peaks at 2 theta, 15, 16, around 15, 16, 22, and 35 degree. These peaks show the characteristic structure. Amorphous areas or non-cellulosic components can be seen at any intensity angle of around 2 theta 18 degree, where crystalline areas or cellulosic components can be observed at an intensity angle of around 2 theta 22 degree. This is also the crystallinity index of the rami fiber after treatment, where all treated rami fibers exhibit a higher crystallinity index compared to untreated rami fibers. This indicates that the chemical treatments increase the crystallinity index of the rami fibers. These results reveal that the chemical treatments are proven to increase the crystallinity index of rami fibers. This is due to the removal of amorphous regions such as hemicellulose, chemical treatment increasing in the crystalline regions. The same trend where the lowest malic acid concentration or 2% have the lower density and less stiff. However, when compared with sample without treatment, the tensile strength of sample Ma2 is than Ma0 or without treatment, with an increase of 3.69%. After the malic acid concentration was increased up to 6% or sample Ma6, first region was fibrils could be reorganized compactly, as shown in same results. Nevertheless, the primary structural elements of the fiber were merged in a malic solution with a greater concentration. For thermal results, we can see that at the initial temperature up to 100 degree, around 100 degrees Celsius, there is a mass reduction in the treated and untreated rami fibers of the water content in the sample. We can see there is decreasing in the region of 100 degrees Celsius. It occurs due to depolymerization of amorphous areas such as. In addition, at this stage, the glycosidic linkages in cellulose are also broken, and the decomposition temperature changed due to chemical treatment on natural fibers. For TGA or DTG results, we can see that the initial degradation temperatures of all sample respectively were around 328.1 degrees Celsius until 333.2 degrees Celsius. This suggests that the Ma6 initial degradation temperature among all samples, indicating the best thermal stability. The highest Tmax or maximum degradation temperature is shown by the fiber treated with 6% malic acid. A higher cellulose and lower amorphous contents the thermal stability of the rami fibers. In SAM, we can see that for the figure A, it can be seen that the fibers have a smooth and dense surface and are covered in many layers of oil wax materials. Where the figure B is for the sample Ma2 or 2% malic acid, show an increase in surface roughness and the start of fibrillation. Where the figure C for sample Ma6 has been shown to remove most surface cellulosic substances. Okay, this is my presentation. If you have any question, please contact me. This is my email and WhatsApp number.
Yeah, thank you, Henny Prathivi. Thank you for the wonderful presentation. Any questions to Henny Prathivi? Have any questions? Yeah, I think there is no questions, Henny. Please text your email ID here in the chat box. If yeah, there is a question from Venkata Siddhartha. What should be a moisture value?
The moisture value is the amount of water the sample could absorb. So the lowest the moisture content, the better the materials. Which in this research, I found that the sample with immersed in malic acid 6 weight% show the lowest moisture content.
Yes, we got the answer. Yeah. Any more questions? No. Yeah. Thank you, Henny Prathivi. Thank you for the wonderful presentation and thank you for joining us today. Thank you very much.
See you.
See you. Yeah, we'll move on to our next presentation. I would like to call upon Zandil Pupa. She is from University of the Western Cape, South Africa, and her presentation is on the title Structural, Magnetic, and Critical Behavior Properties of. Hello.
Hello, everyone. I hope everyone is well. First, I would like to apologize because we have a situation in South Africa of the protest against illegal immigrants. So I will have a little noise because I have a little one around me.
Yes. Yeah, I permitted you to share your screen. So,
Okay. Where should I share the screen?
yeah, below there is an option share. So just please click on that.
Oh, share. Is it sharing though?
Yeah, sharing your screen, share your presentation, PPT.
Okay, let me go back. Hello, can you all see my screen?
Yes.
Yes. So my name is Zandile Mpupa and I'm doing PhD in physical science at University of Western Cape in South Africa. And my title is Structural, Magnetic and Critical Behavior of Properties of Cerium, Aluminium and Germanium with a composition of 234. We are doing the research on rare earth material and we chose the cerium so far because I'm still in the middle of my research. And why we interested in the rare earth materials? My outline for my presentation will be introduction, crystal structure, magnetic properties, heat capacity, and critical behavior study, and the conclusion. So why are we interested in rare earth materials is because we know that rare earth materials they have magnetic properties, and that's why we are interested in them, and they are able to conduct electricity. And so since the study is of the tenured intermediate compound with a composition of 2,3,4, I just said that we're focusing on the periodic table. We know that rare earth materials are the ones that are on the bottom. So I'm focusing now on the first one, which is cerium, the ones that are magnetic, not the ones that are non-magnetic, like lanthanum. And we mix them with the transaction metals and the p block elements, and we want to see if they can be able, after combining them, they can be able to conduct electricity or be able to continue being magnetic. So, and these properties, to be able to see, there are types of properties that we can find in magnetism. There's antiferromagnetism, ferromagnetism, Kondo interaction, heavy fermion behavior, and the spin class anomalies, and the magnetic effect. So my objective, or the importance for this research, was to study the magnetic properties of this compound, my compound of cerium, and other compounds that I will still focus on in my research as I go to understanding the fundamental origin of magnetism and electronic correlation in rare earth intermetallic compound of cerium 2 aluminum 3 germanium shows that my compound is actually ferromagnetic ordering and critical behavior. As I'll continue, you will see why am I saying this, and developing a functional magnetic material for energy efficient cooling technology like refrigeration technology. So my samples, how I prepare my samples, my methodology is how I prepare my samples. So I will have a cerium which stays in an, it doesn't have to be exposed to an oxygen. Once it's exposed to an oxygen, it evaporates. So I cut them into small pieces and using their composition, and mix them with aluminum and germanium compounds. And the purity of each element is, for cerium is 99.8%, and continue to germanium, which is 99.99%. And these compounds, once I cut them, and then I will be able to use the arc furnace to melt them at a higher temperature of above 500 degrees Celsius. And then we assume that the mass of an ingot, because we use our samples, we measure them to be 3 grams, but we know that after heating them, they will lose some mass. So we expect that the mass they should be lost, it should be less than 1%, which for in my case, my samples was less, it was 0.12%. And then after the sample was melted and combined, we therefore go for us to be able to continue to measure the magnetic, we must be able to see the quality, to know the quality and the quantity of the compound that we got. So we then do the characterization of powder, SRT, measurement using the machine that we see on the screen. And then we measure from 15 degrees to 90 degrees. And then for there, we use the Topaz Academy for analysis to be able to analyze and see if all the peaks, or we have impurities in our samples, or we don't have impurities in our samples, or we do have a good quality that we can continue to do the other characterization, magnetic characterization. And then after that, after we found that it was good, and then we can be able to use now to measure the magnetic properties and the heat capacity. To measure the reason to measure these things is to find out if our material is antiferromagnetic, ferromagnetic, or ferrimagnetic, or it's actually non-magnetic at all. So we can be able to measure these using this machine, which is the physical properties for magnetic measurements. And then going to results and discussion, we then did the SRT, and my SRT for my sample, which is the cerium, aluminum, germanium, and this is the crystal structure that I got. And this crystal structure is orthorhombic crystal structure, And therefore, with the previous research, my compound exactly aligns with the previous research of other scientists that they've done this research, are not using my samples but using other samples, other types of samples. So I can say that looking at my SRD with the green symbols representing my experimental data and the red symbol representing the calculated diffraction patterns, they all align and there's no peaks that was left behind, or I can say there's no impurity peaks. And then the gray lines represent the difference between the peaks. And then that means I was able to I can say that my crustal structure is a single phase orthorhombic structure with a spread group that I was using, which is the CMCA. And continue to say that, okay, looking at the crustal structure and looking at other people who were using composition of 234, they were able to see that it was ferromagnetic. But now using the SRD alone, I can't say clearly that this is ferromagnetic. So I have to continue measuring at DC magnetic susceptibility. And looking at my structure, I have on the left, I have the magnetic susceptibility that was measured at a temperature of 1.8 Kelvin to 300 Kelvin. So now I can't clearly see what's happening. I can say that above 40 Kelvin, my samples reach saturation. So I can be able to use the Curie-West law using the inverse susceptibility, which is my graph on the left. Now, I had to again to be able now, because I noticed that in my samples at a lower temperature that is less than 40 degrees, it gives me two magnetic ordering, two transactions that are happening there in a lower temperature. So I had to measure my susceptibility at AC. And then I get two transactions, which is the first transaction, which is T1, and the other one is a Curie temperature. And the first transaction, it can be a rearrangement of the magnetic transaction order. And then after that, I can be able to use the Curie-West law to be able to calculate my magnetic moment. And what I got on my magnetic moment, it was less than what the theoretical magnetic moment was given. Because what I got for my magnetic moment, I got 2.18, 2.128, and then the theoretical is 2.54. And I can say that it is true, maybe it might be true that it is crystal electric field effect, or maybe there is a possible condor screening or some other magnetic transaction that are happening. But then I continue working at a lower temperature to find out where my exact TC is, and the other using I did the derivative to find out at a lower temperature, where is my Curie temperature. And then using this, I can tell now, and I had to measure the magnetization to indicate the incomplete saturation, and the strong magnetic isotropy. I can see that it's lowered my magnetization rapidly, grew faster, and then after that, after some time, I can see that at a higher field, it will reach a saturation. And then I continue, but now with the susceptibility, I was able to conclude that my samples is actually ferromagnetic. And then after that, I continue to do heat capacity, because I can't confirm with one characterization that my sample is ferromagnetic or antiferromagnetic, because in a susceptibility, I was able to see that even though my theta p was negative, it was supposed to be antiferromagnetic. So there's a lot that is happening with my samples using the susceptibility alone. So I had to continue using the heat capacity analysis. And then with the heat capacity, I see that now I have two phases in the heat capacity. The higher temperature above With the heat capacity above 40 Kelvin, I can see that I can be able to use the Dubai heat capacity, which has a phenon heat capacity and the Dubai heat capacity. And I was able to find the fitting parameters, which aligns exactly with what the theoretical or the literature review can show me. And this also indicated that it is indeed the ferromagnetic that I was using. But now at lower temperatures, I also saw that there are two peaks or two transactions that are happening at lower temperature. So it also shows me that now at lower temperatures, at lower temperatures, I was able to see that now I have TC and T1. So even the heat capacity can confirm that I have a ferromagnetic ordering in my sample. And then after that, the lines that I see here, the dotted lines, are called Dulent Petit, and I was able to, my apologies. And then I saw that my samples aligns exactly with the Dulong Petit. And then as I confirmed that I had two ordering, which is the TC, which is the ferromagnetic ordering, and the secondary magnetic transaction, which is T1. That was shown on my substability, and it was shown on the heat capacity. So now I can be able to confirm that indeed my samples was ferromagnetic. But now I had to continue because I can be able now to measure, or I was able to measure at different field and to see where I can be able to see the spin wave at low temperature and high temperature. And the differences was very small, the differences, as I see using the spin wave equation, that there's a small difference looking at the spin wave parameters. And then now I can say that the change or the differences, this can be reduced by Magnon contribution. And then after that, I was able to continue because now I actually know from the magnetic susceptibility and heat capacity that my sample is ferromagnetic. Then I can do more with my samples. And then I had to measure the isothermal magnetization and then you're looking at the magnetization, isothermal magnetization. This is depending on the temperature from 3 to 15 Kelvin with a step of 1. I can see that as the field increases, they become more like straight lines. So I had to continue and do what they call arrow plot, because now I can see that as it continues, it will reach a stable or a saturated part at a higher field. So I was able to go and do the arrow plots because now I can be able to do analysis of what's happening in my samples using the universal class models. And I first did using the mean field model, which is the normal one. When I did the mean field model, I was able to modify it. And then I get my beta, my exponential constant, which is beta and gamma, and they were more close to the mean field. But now I couldn't conclude that it was indeed a mean field model. So I had to continue and do other models to conclude. And then now it shows that my samples was a mean field model, which is satisfying the Bennier criterion for a second order ferromagnetic transaction. So now I can know that this is a second order transaction for a ferromagnetic compound. And then I had to continue with my critical exponent to calculate to get the exponents. I had to use what we call the linear lines, the red lines. I had to get the linear lines to be able to get the exponents that you see, the beta 0.6 and 0.98, to be able to conclude if my samples is a mean field model, or it's a Eisen 3D Eisen model, or is it a Heisenberg 3D Heisenberg model. And then I had to continue after that, even confirming that it's a mean field. But now I have to do other method, which is a cover feature, which is the graph that is below here. And in the cover feature, it's clear show that my gamma is 1.1. While in a mean field, we know that it was 1, gamma was 1. So I can say approximately my sample has a gamma of 1 and my beta is 0.6, which in a theoretical in a theory of a mean field, beta is 0.5, which is close to the mean field. I can conclude that my samples is close to the mean field. So now has a second order magnetic transaction or ferromagnetic transaction. So now I had to investigate using isotherm for critical exponents to investigate near TC. What is happening near TC? And now I had to do what we call a critical exponents and a widow scaling, which is this one. And when I did the critical exponents, which is sigma, I was able to get the value of 3, and then which is very close to when I'm using the equation of the widow scaling, that is close to 3. So now I can indicate that the long range for magnetic interaction, it was indeed a mean field. My sample was in a mean field using the scaling. And now I must be able to investigate what's happening with other isotherms that are near or below or above TC. And I had to use the scaling collapse, which is the Widom scaling. And then here I can see that at the red one is the magnetic, but I was able to see that all my graphs, they actually collapse into two curves. That is above the TC and below the TC. And I was able to see that my samples obeys the scaling hypothesis, which I can now conclude that it is a second order phase transaction, and the correct critical exponents are reliable when we're determining TC. And in conclusion, I can now say that I was able to, for a crystal structure at room temperature, confirms the orthorhombic crystal structure with a space group of CMCA. And for magnetic transaction, I was able to confirm that my sample is ferromagnetic phase transaction that is below the Curie temperature. And there's an additional transaction, which is T1 for the direct current and the applied current of subsibility and heat capacity. And then now I can also be able to confirm that the critical behavior, it was well described, because I was doing the critical behavior, it was well described by the 3D mean field universality class using the exponents that are close to the mean field. And to continue, I have to still continue to use the magnetochiralic effect to highlight the potential for low temperature magnetic refrigeration applications. And these are the people that I was using to reference on my work too. And I would like to acknowledge the NRF and the UWC for giving me this chance, and the UJ. And thank you. Hello.
Yeah, Thank you for the wonderful presentation, Zandil Pupa. Yeah, any questions to Zandil Pupa? You have any questions? Yeah, there is a question where this material can be applied, like practical applications.
So far, thank you for the question, but so far we haven't done the practical applications. Um, but I think it can be done on the refrigerations, using for refrigeration to check if we can be able to, because most of the refrigerators, they need a higher magnetic elements. So I think we can be able to use it there, but we haven't done any applications. I'm just a research-based person. Even my supervisor said we just theoretically researchers, so I can't say.
Okay. Yeah, any more questions? Yeah, there is no more questions. Zandil Pupa, thank you for the wonderful presentation and thank you for joining us today. Thank you very much.
Thank you so much for giving me this chance. Thank you.
Thank you. And we'll move on to our next presentation. I would like to call upon Miriam Takauli. She's from Muhammad V University, Morocco. And her presentation title is Green Hydrogen Production through Water Electrolysis, Challenges and Future Opportunities. Miriam, yeah, I permitted you to share your screen.
Hello, everyone. Can you hear me?
Yes.
Okay, great. Can you see my screen?
Yes, I can see your screen. Yeah, please go ahead.
Okay. Okay. Good morning, everyone. Thank you for giving me this opportunity to present my presentation. First, let me introduce myself. My name is Mariam Tawkil. I am a master's student in analytical science, quality and environment in Mohammed Zank University in Rabat, Morocco. And currently, I am a research intern at the National Laboratory of Engineering Civil in Lisbon, Portugal. And it's my pleasure to present my presentation entitled Green Hydrogen Production Through Water Electrolysis, Challenges and Future Opportunities. Here is an outline of today's presentation. First, I will introduce the concept of green hydrogen. Then I will explain the main technologies, pathways, and the principle of water electrolysis. Next, we'll move to the main electrolysis technologies, followed by benefits and current challenges and future opportunities. And finally, I will conclude with a conclusion. This slide illustrates the global energy transition. In the past, energy production mainly depended on fossil fuels, which caused high CO2 emissions. But the future and today, many countries are shifting towards renewable and low carbon energy system, such as green hydrogen is expected to play the important role in supporting this transition and achieving a more sustainable future. So why green hydrogen is very important? It's very important because first it produces from renewable electricity and water and water, and also it almost generate no CO2 emissions during its production. Also, it helps to store renewable energy and it can reduce carbon emissions in a lot of sectors such as industry, transport, power generation, and etc. So this is why we can say that green hydrogen is considered one of the most promising clean energy solution. Let's classify hydrogen by its color. Of course, there is many colors, but today we'll focus only on three colors that is most that we most used. Let's start with gray hydrogen. Gray hydrogen is currently actually the most widely used type of hydrogen. It's mainly produced from natural gas and other fossil fuels. However, as you can see in this figure, this process it releases a large amount of carbon into the atmosphere. Although it's cost effective, it's not expensive, it's cheaper than other technologies, but it has high environmental impacts and it's not considered a sustainable solution. This is why the transition toward green hydrogen is becoming very important. The next type of hydrogen is blue hydrogen. It's like green hydrogen, it's produced from natural gas, but the main difference is that the emission of carbon dioxide generated during the production is captured and it's stored using carbon capture and storage. So as a result, we can say that blue hydrogen lower carbon emissions than the gray one, but it still relies on fossil fuels. So it's not completely carbon free. This is why we should generally consider a transition technology towards green hydrogen. So finally, we have green hydrogen, which is considered the cleanest type of hydrogen. Unlike green or blue hydrogen, it is produced using renewable electricity such as wind or solar energy through water electrolysis. So as a result, it generates almost no carbon emissions during the production. So for this reason, green hydrogen is considered a key solution for achieving a sustainable and low carbon future. This slide illustrates how the role of renewable energy in the production of green hydrogen. We can use solar or wind and hydropower, which provide the electricity needed for the electrolysis. And during this process, water is split into hydrogen and oxygen. So renewable energy is very important because it allows us to produce, sorry. So, yes, I said that the renewable energy is very important because it allows us to produce green hydrogen with no carbon emissions. For example, solar energy it's a good option in region without strong sunlight, such as in North Africa or Southern Europe. So we can say that green hydrogen can be stored, can store this electricity, and after we can use it in many industries such as transportation, and therefore we can say that green hydrogen and renewable energy can support each other in the energy transition. And now let's move to the next slide. Let's see how can we produce green hydrogen. We can produce it through the electrolysis. So the principle is simple. Electricity is used to split water into hydrogen and oxygen. Hydrogen is generated at the cathode and the oxygen is generated at the anode, as shown by this reaction. Two water molecules produce two hydrogen molecules and one oxygen molecules. The hydrogen obtained can be stored while as a clean fuel, while oxygen is released as a byproduct. Electrolysis has many technologies. The first one is alkaline electrolysis. It's the oldest and most widely used technology for hydrogen production. It uses a liquid alkaline electrolyte, usually potassium hydroxide or sodium hydroxide. Its main advantage as its low cost and also long lifetime, and it's proven the reliability. It's making it sustainable for large-scale hydrogen production. However, it has some limitation. For example, it uses lower current density, and it's a slower response to fluctuations in renewable electricities. The second technology is PEM electrolysis, which stands for proton exchange membrane. It's unlike the first one. It uses a solid polymer membrane instead of liquid electrolyte. This technology, it produces very high purity of hydrogen, and it has the compact design. But the problem is that let's talk about the advantage. Its advantage is that it's fast response to changes in renewable electricity. So that's make it ideal for solar and wind power. But its disadvantage is that the electrolysis is more expensive when we use it because it requires precious metals catalysts such as platinum and iridium. Many countries now interested in green hydrogen because it provides several environmental benefits. First, it produces almost no carbon emissions. It helps to reduce climate change, and also it improves the air quality by reducing the use of fossil fuels and lowering harmful air pollutions. Also, it uses renewable electricity and water. It supports cleaner and more sustainable energy system. Besides the environmental benefits, green hydrogen also offer economic energy advantage. It can create new jobs, it can promote clean energy industries, and also it encourage investments. So at the same time, it helps to store renewable energy, it's improved the integration of solar and wind power, and also it strengthens the energy security for the countries. That's why many countries are investing a lot in hydrogen technologies and also its infrastructure. For example, the United States, it's investing in clean hydrogen hubs and infrastructure. The European Union is supporting large-scale hydrogen projects through funding and strategic initiatives. China has experienced rapid growth in hydrogen production and application. And finally, Japan is a pioneer in hydrogen technologies and international partnership. So that's demonstrate the increasing importance of hydrogen in achieving a sustainable energy future. So together, these global efforts are accelerating the transition towards a cleaner and more sustainable energy economic. Although green hydrogen has many advantages, but it has also a lot of challenges. The first challenge is high production costs. This challenge is one of the biggest challenges. It's expensive because it depends on renewable energy and electrolyzers. The high cost of the electrolyzers also, they are very expensive. However, technological progress, larger production capacity, and economic of scales Also, the costs of green hydrogen is expected to decrease in the coming years. The second challenge is hydrogen storage and transportation. Hydrogen has a low energy density, so it must often be compressed or liquefied before its storage, so that increase the costs and require careful safety measures. In addition, transporting hydrogen might require dedicated pipeline and new infrastructure, and that's making large-scale development more challenges. The third challenge concerns infrastructure and energy demand. Producing and distributing green hydrogen requires pipelines, refueling stations, and major investment at the same time. Electrolysis requires large amount of renewable electricity. Therefore, expanding renewable energy capacity and balancing electricity supply and demand are essential for the successful deployment of green hydrogen. The final challenge is water availability and also quality. Producing green hydrogen requires a significant amount of purified water, and its quality is essential for efficient electrolysis. Poor water quality can damage the electrolyzer and reduce its performance. Therefore, solutions such as water treatment, desalination, and water recycling are important to ensure sustainable hydrogen production. Despite this technology, significant technological progress is being made in green hydrogen production. Researchers are developing more efficient electrolyzers and advanced catalysts to improve the performance. In addition, new technology help reduce production costs while increasing efficiency by producing more hydrogen with less energy. So as a result, green hydrogen is becoming more competitive, and it's expected to play an important role in the future energy transition. Green hydrogen has a wide range of future application. In transportation, it can power zero-emission trucks, buses, aircraft, and ships. And also in industry, it can help to decarbonize sectors such as steel, cement, and chemicals. It can also store renewable energy for later use and improve grid stability. So in the future, green hydrogen is expected to play a key role in smart cities and integrated hydrogen ecosystems. So supporting the transition to a carbon neutral energy system. In a conclusion, we can say that green hydrogen is much more than alternative fuels. It's a promising solution for decarbonizing industry, transport, and energy sector. Although several challenges remain, continuous innovation and global investment are accelerating its deployment. So with ongoing technological progress, green hydrogen is expected to become one of the key pillars of a sustainable and carbon neutral future. Here I finish my presentation. Thank you very much for your attention, and I would be pleased if you have any questions.
Thank you, Mariam. Thank you for the wonderful presentation. Any questions, please? Yeah, there is a question. Among the future applications you presented, which sector do you believe is most likely to achieve large-scale commercialization first? And what are the biggest technical and economic challenges that still need to be overcome?
I guess that the question was is about which sector we should use more hydrogen, right? Will benefit more from using hydrogen.
Yeah, I'll go through the question once again.
Okay.
Among the future applications you
Okay.
presented, which
Yeah.
sector do you believe is most likely to achieve large-scale commercialization first? And what are the biggest technical and economic challenges that still need to be overcome?
Okay, I think that the future application, it must be in the industrial applications, such as the cement factories. They are using a lot of now, for example, in the oven, they use a lot of uh, uh, power, and that release a lot of dioxide of carbon in the air. So by using green hydrogen, it's gonna be a good solution for that problem. And also about the challenges, I think that we must secure a lot of wind power and solar power, and also we must develop the infrastructure. For example, we must have a lot of fuel station for green hydrogen, and also upgrade our infrastructure in many countries. So this is the big challenges for now, in my opinion.
Yeah. Yes. Any questions? I think there is no more questions. Thank you, Mariam. Thank you for the wonderful presentation. Thank you for joining us today. Thank you very much.
Thank you so much, and I would like to ask you for giving me the opportunity to present this presentation.
Thank you. Yeah, and we'll move on to our next presentation. I would like to call upon Venkata Siddhartha. He's from Teesside University, UK, and his title of presentation is Repurposing Natural Gas Pipelines for Hydrogen Transport, Material Selection, Finite Element Integrity Assessment, and Customer Adaptability Analysis.
Yeah. Hi. Can you hear me?
Yes.
Yes.
Yeah, I permitted you to share your screen, Venkata Siddhartha.
Just a minute. Can you also give permission for my other Venkata Siddhartha Sharma, because I'm using both phone and computer? Yeah, got it. Thank you. Just a minute. Can you see my screen? Hello? Hello?
Yeah, I can see your PPT, Venkata Siddhartha.
Yeah, that's fine. Thank you. Right. So first of all, thank you for the organizers and researchers, masters, all participants, guests. So my name is Venkata Siddhartha Sharma. I'm currently pursuing my PhD in material science. I just started in March 2026. And my director of studies is Dr. Manu Ramegowda. And I'm from Teesside University, UK, School of Computing, Engineering and Digital Technologies. Today, I'll be talking about my project. It's mostly related to the green hydrogen pipelines. You already heard from the last researcher about the challenges of green hydrogen. So specifically, I'll be talking about challenge number 2 in her presentation, pipeline transportation and storage. Predominantly, I will talk about transportation. So the title here is Repurposing Natural Gas Pipeline for Hydrogen in Teesside region, UK. So repurposing, the definition of repurposing means we are trying to use the natural gas pipeline and we are trying to send hydrogen in it instead of natural gas pipeline. So that's the definition of repurposing. Some of the contents, I'm going to touch upon background, problems, aim and objectives, some challenges, material selection, and what's my research novelty, methods, some case studies, and importance and benefits of this research. So coming back to the background, so net zero has been talk of the town in almost all countries, and set of rules were also been laid in order to implement net zero by 2050. And so there are some 8 rules. So predominantly I will be touching on number 8, which is to build pipelines specifically for hydrogen gas. So in the graph, if you see a graphical representation, so here in UK, we are trying to repurpose natural gas pipeline for a distance of 20 kilometers and using diameter 500 mm and pressure 70 bar. If you compare with the other countries like USA and the EU, USA has already done some sort of research and some sort of implementation for the 983 kilometers with a diameter of pipe 360 and pressure 50. EU, in which all the countries like 1600 kilometers, and they have used 168 diameter, pressure of 100. But we are trying to use higher diameter, as you can see 500, which is higher than 360 and 168. And we are trying to use pressure 70, like a balanced pressure. Most important problems, these are the most important problems. When you are trying to send the hydrogen gas in a natural gas pipeline, which is completely different because natural gas pipeline is meant to be used for natural gas, but we are trying to send hydrogen gas instead of natural gas, which means there will be some technical challenges. I'm sure you already heard of the previous researcher talking about challenges, technical challenges. So these are the technical challenges. The most important technical challenges is leak. And then second one is stress cracking. Third is corrosion. And then fourth is some welding failures. And then fifth one is you can also see some pipeline damages due to some corrosion or some coating degradation. On right hand side, you can see as another pictorial representation of a defect, a major problem, which is called hydrogen embrittlement. So the left hand side, these 5 defects are related to pipe defects. The right hand side image is related to the hydrogen defect, which is hydrogen embrittlement. So what happens is when hydrogen is sent inside the pipe, the hydrogen molecules go inside the pipe and they touches the grain boundary and then the defects started arising like crack propagation, crack initiation, all those stuff. So the aim of the project here is X52. We are trying to take X52 material, which is a steel again, high strength steel, and we are trying to optimize the operational parameters of X52 so that the defects which you saw, the hydrogen defects like hydrogen embrittlement and the mechanical defects like all those 5 defects can be optimized. So we are trying to fix the operational conditions. We are trying to know in which operational conditions these defects will be optimal, where it doesn't increase or doesn't decrease. So that's the main aim. So how are we going to fix these operational parameters? That's the objectives. The focus is on, as I said, we are trying to minimize the hydrogen defect, which is hydrogen embrittlement, and how we're going to optimize the operational parameters is changing the pressure, changing the wall thickness, changing the diameter of pipe, and lots of case studies. So these are some of the operational challenges which you can expect when you send hydrogen gas in a natural gas pipeline. So in today's presentation, the first you can see an arrow put it that is pressure related, so overpressure. So in this research, we will try to do all these operational challenges there will be leakage issues, blockage issues. We'll touch on all these operational challenges, and we'll try to optimize, uh, and we'll try to give a data which what is the optimized operational parameters so that these challenges is mitigated. So coming back to the material selections, obviously you can use X42, X46, X52, X56, X60, X65, X70, X80. These are all the steel materials. Still, they're all high strength steel. But why we are only using X52 in this research? And the answer for why we are only using X52, why can't we use X56 or X60 or X65? Because all the UK natural pipelines, majority, they're all made up of X52 material. So we are not changing the material of the pipe. Everything will be remain as it is. It's just we are trying to send hydrogen instead of natural gas. So X50 is cost effective and is being currently used in natural gas pipelines in UK. So this is my research novelty. So in the beginning, you saw the defects slide, the pipeline defects as well as the hydrogen embedded defects. So how we can minimize these defects, especially the hydrogen embedment one. So for that, we came up with a plan, a kind of a mitigation step, that is to use coating. So you can see from the middle picture, uh, we are trying to analyze what will happen to the hydrogen embedment when we use single layer coating. What will happen when we use multi-layer and microalloyed multi-layer, and then microalloyed multi-layer plus corrosion film protections. So these are some of the mitigation steps we came up, and additional mitigations such as inhibitors uh, also comes into the picture. So so these are the mitigation steps. Everybody, we try to come up with some sort of steps. So eventually, this is a practical research. There will be some practical defects as well. So steel pipe, when it's come to the implementation, there will be some practical defects like welding issues or some minor cracks or some micro cracks. So that also needs to be mitigated. So practical defects like welding, steel processing defects, and some auxiliary parts defects. Because auxiliary parts means sometimes steel will not be straight. There will be a curved steel or a L joint steel. You will see those different types of auxiliary parts. So we also need to take care of those auxiliary parts. So the first objective is the operating parameters. I have said we will check, we'll try to change the wall thickness of the pipe, pressure, diameter of the pipe, and see which parameter is actually suitable in order to mitigate the hydrogen embedment, and also the welding characteristics. These are the first objectives. The second objective is and steel processing. The coating layout. So this is the most important. So this is how we came up. So the gray color, which you are seeing, that's the pipe. And the top is the epoxy coating, which is the corrosion film protection, and nickel alloy coating and alumina barrier coatings. So these are the two coating materials we came up at this stage to use in order to mitigate the technical challenges like hydrogen embedment and cracks. So this is the methodology. So we started with the data gathering, with the literature, and then we used a tool called Finity Element Analysis. There is a software by Siemens. So using that software, we can um, we can uh, we can see whether there is any mechanical damages of the pipe or not, and then after that, you can see the case studies. We'll run some case studies. I will show some case studies as well. After case studies, um, we will try to do coating because that's the most important. When you coat it, and if the pipe is still intact, if the pipe does not show any crack, then it's good. If it is showing, then we have to again change some coating parameters. So hydrogen embedment is next important, And then the collaboration, you can see at the left side, red color, collaborative outcome, industrial results with experimental tests. So we are planning to collaborate with some industries to know some practical defects. I have told you before, when steel is made, some steels are made, there will be some manufacturing defects. So we also need to consider those defects and how it will impact our hydrogen defects. So we have to collaborate. We are planning to collaborate with industries, and then obviously then we'll get a final report of X52 uncoated, and then then we can see the same cycle with the coating as well. And the geometry. So this is the geometry. So the pipe is not straight here. It looks like an S because in practically none of the pipes will be straight. They have to take some turns because of the locations. So we'll be using this sort of geometry for FEA analysis. Okay, so these are the pipeline parameters. So the first one is the most important. We'll be checking we'll be changing the diameter, thickness, welding characteristics, and also we'll changing the internal pressures, operating conditions, temperatures, flow velocities. So on the right hand side, you can see some of the test, mechanical test, hydrostatic test, weld test. At this stage of the project, we are trying to check mechanical test. We are not doing the hydrostatic test, maybe in the future, but we are trying to do mechanical test in the beginning. And then obviously we'll do some inspections in the monitoring with having a collaboration with the industry. So these are some of the case studies. I have told you that we have collected data and we'll be using finity element analysis tool to check whether there will be any mechanical damage to the pipe or not. And these are some of the case studies we have developed. So case study 1, case study 2, case study 3. So in the case study 1, you can see the outer diameter is 800 mm, wall thickness is 150 mm, and we have used some coating, outer coating epoxy 5 mm, inside coating epoxy 5 mm, and pressure 80 megapascal. But we changed from case study 2. We have not taken 800 mm outer diameter. We have used 300 mm outer diameter. Why? Because 300 mm diameter is actually diameter that is used practically, not 800. So we changed it. So, and you can see from the case study 1, the maximum, the orange color, the maximum stress is 116.42. And from case study 2, the maximum stress is 404.51, which is high, very high, maybe because of the coatings. And the case study 3, where there is no coating, uncoated one, which shows 110.56 megapascals of stress, maximum stress. So this is the case study 2. So I'm going directly from the case study 2. We are not touching case study 1 because it's a failed case study. Why? You can see in the bullet point, though from the case study 1, the maximum stress is only 116.42 megapascals, it was still had not been considered for all future research. Why? Because in practical pipeline, you won't find 800 outer diameter and 150 mm wall thickness. So we have decided not to go forward in our research using case study 1. So we only consider case study 2 and case study 3. So the pictures which you are seeing is case study 2, which has nickel coating 5 mm inside and epoxy 5 mm thickness outside. And the outer diameter is 300 mm, 25 mm wall thickness. So on the right hand side, you can see the maximum stress is 404.51, which is too high. It's high. And that can affect the safety of the pipe. The pipe can break. The pipe can produce some crack. So in later case studies, the thickness of the coatings will not be 5 mm. It will be 1 mm or less than 1 mm. So in later case studies, that will be decreased. So factor of the safety. So this is where most important, factor of safety and hoop stress. and this is for the case study 2. So though case study, I mean, you can see for 20 wall thickness, the hoop stress is 480 megapascal. The hoop stress cannot be ever high than the ultimate tensile strength of X52. See here, the 480 megapascal is greater than 460 megapascals. If it is like that, the pipe will not withstand the hydrogen. It will break. So always the hoop stress needs to be less than the 460. So, and you can see in the bullet point, the factor of safety, the formula is yield strength divided by maximum stress. So the yield strength of X52 is 360 and the maximum stress we achieved is 480. So 75 factor of safety, which is very low. The factor of safety at least needs to have 3 in order to put hydrogen in a natural gas pipeline. 0.75 is very low. So the pipe is not safe under these conditions because of the maximum stress obtained 400 megapascals, in which there will be a plastic deformation. So that is why case study 2 is also not suitable. Now, case study 3. So after saying case study 1 and case study 2, we came up with case study 3. Okay, with some changes. In the case study 3, we have kept the diameter of the pipe 300 mm as it is, but we have not used any coating, completely 0 mm. And pressure, instead of using 80 megapascals, I'll just show back this. So instead of using 80 mega applied pressure 80, we only used 7 and 10, mostly 10 megapascals. Material is same. So the factor of safety after using these parameters is 4.160, which is very high. We got how much? 0.75 in case study 2, but in case study 3, we achieved 4.160. And please be in mind, this is uncoated one, it's not coated. And the right side, the 2 figures which you are seeing, this is for the state pipe. And these 2 figures, the smaller figures which you are seeing, they are called elbows. They are the auxiliary parts. So in those auxiliary parts as well, the maximum stress is not high. It's 78 and 111. So from the case study 2, you can see in the bullet points, both factor of safety and maximum stress is not higher than X452 ultimate tensile strength. Therefore, the pipe can withstand its mechanical properties for manufacture mechanics breakdown. So this is a major breakthrough which we found it. After decreasing the pressure from 80 megapascals to 10 megapascals and also decreasing the diameter of the pipe from 800 mm to 300 mm, we could able to achieve good factor of safety, which is 4.160. And that came from the case study 3. Again, after getting that information, after getting that sort of result, we continued with the case study 3, but we want to also see how the pipe will behave if there is any change, if the pressure is applied gradually. No? Gradually in the means step by step. So in continuation with case study 3, by using same pipeline parameters, non-linear analysis is performed to know the stress behavior when pressure is applied gradually with respect to time. So as you can see in the table, so for time 0 second, the pressure is 0. And for 1 second, the pressure is 4 megapascals. And for 2 seconds, the pressure is 7 megapascals. So you can see 0, 4, 7, the pressure is kept gradually increased. It's not like sudden from 7 megapascals. And the respective maximum stress we could be able to achieve for 0 megapascals is 22, for 4, 42, and 7, 59, which is very good because they are less and lesser than the tensile strength of X52. But the most important point here is, however, if pressure increases, say for example, if we increase the pressure to 20 megapascals, then the stress will increase. If the stress increases, then we can expect some mechanical breakdown of pipe. So it is very, very important to optimize the pressure. The pressure should be 7 or 10 or below 10 or below 7. That's fine. If it is more than 10, then there is a problem. So the conclusion. So from the case study 1, cannot be considered as dimensions are not realistic as per industry standards. So we have eliminated case study 1 because in practically 800 mm diameter of the pipe, there is no such kind of dimensions. Case study 2 also cannot be considered because of overpressure, right? 80 megapascals pressure is very is very high. With that high pressure, the pipe can deform and can result in some massive crack and massive breakage. And also the thickness of coating should align with industry practices. Thickness we took 5 mm, which is highly cost effective, highly cost. Uh, so industries don't use 5 mm coating thickness. They would like to have somewhere around 1 mm coating or less than 1 mm. So the case study 2 also cannot be gone forward. So from linear and nonlinear analysis uncoated, we could able to achieve factor of safety over 5.83, which is case study 3. And my future work will be checking. I'll repeat the same analysis. I'll use the case study 3 only, but I will try to apply coating which has a thickness less than 1 mm or less than 2 mm and see how the pipe will behave. After that, we'll use another software called CFD, Computer Fluid Dynamics. So where hydrogen is actually sent, you can see in the pictures, red, green, and blue. So you can see so we'll study the fluid dynamics of hydrogen when it is inside the pipe. And also we'll add some manual crack in the software, and we'll see how it is behaving when there is a crack. So these are some of my future work, which we are doing it. Yeah. So finally, one of the major importance and benefits of this research is if anyone who wants to invest a new hydrogen, what you call storage, production, transmission, it's a cost. It's a highly cost. So if you use an existing natural gas pipeline and try to repurpose it for green hydrogen, that will save lots of money. So nearly 14 to 16% you can save from your capital cost. So it saves huge capital cost. And the major breakthrough is from this research is you could able to exactly know what is the mitigation strategy to optimize hydrogen defects. The slide which I shown you in the beginning, hydrogen defects such as hydrogen embeddment and the mechanical defects like leak, cracks, and all pipe cracks. So the mitigation strategies that's the major breakthrough in this research. So I'm always ready for any collaborative research all over the globe. I can travel, and I'm also available and ready to interact with industries across the globe. If anyone wants to know more information or probably also able to spend some time for like mentoring, I'm also happy. We're also looking for any sort of funding opportunity. This research is not funded. We are in a chase to get funding. So the doors are open. Please contact us. My name is Venkata Siddhartha. I'm a researcher. And Dr. Mandu Ramagowda, he is my supervisor and director of studies. These are our emails and contact details and some of the references. If you have any doubts and questions, I'm happy to answer.
Yeah, there is a question, Venkata Siddhartha from Hene Prathivi. Did your finite element model consider cyclic pressure, loading, and fatigue? Since hydrogen pipelines typically operate under repeated pressurization that may accelerate crack initiation and propagation.
Right. So this cyclical loading is next step we are going with the linear loading at the moment. The pressures which the stress which you seen from the FEA results, they're all linear loading. They are not cyclic loading. Cyclic loading is much more complex, and that involves a couple of tools, not only FEA. I told that we'll be touching CFD as well. So we have to use FEA, CFD, and then there is one more software called multiphysics. So we'll be using 3 to 4 softwares to check cyclic loading. So that will be again a complex one, will be a future one. It's not now. We just started this research in the March 2026, 3 months back. So cyclic loading is a very important and it's very complex. It comes afterwards, after 4 or 5 months, but not now. Yeah, thank you.
Yeah, thank you for the wonderful presentation, Venkato Siddhartha. Thank you. And thank you for joining us today. Thank you very much.
No problem. Thank you, Sam. Thank you all.
Thank you. Yeah, we are waiting for the speakers from the USA, so we'll have a break now. Yeah, actually, we waited for a speaker from the USA, so he just stated that he won't be able to turn up. So we concluding the webinar, and thank you all the participants who attended the webinar and for their wonderful presentations today. And so this comes to the end of our 2 days conference, and simultaneously we successfully completed the live conference in Berlin, Germany. And we have been fortunate to have a great identities from academic industries and other areas with us. And we will be glad and thankful if you could join us in our next conference in person or virtually. And the dates will be informed to you by email, and also would request you to share your valuable opinion or feedback with us. Thank you and have a nice day. Bye-bye.
Thank you. Bye bye.
Bye.